Welcome everyone. This is the course on engineering graphics. And we are going to learn about engineering curves in this session. We are going to cover two types of engineering curves, the cycloid and the involute. Let us see what is cycloid. Cycloid is the locus of the points lying on the circumference of the circle which rolls without slipping on a fixed straight line. That is, there is a circle which is rolling on a fixed straight line. The points on the circumference of the circle are going to follow a path that is called as the cycloid. You take any point and trace the path of that point. When it is rolling on the straight line, that path is a cycloid. By definition, that curve is a cycloid. Let us see one example. A wheel of 56 mm diameter rolls on a horizontal floor for one revolution. That wheel diameter is 56 mm. It is rolling for one revolution, one complete revolution on the floor. Draw the locus of point P on the circumference of the wheel. Okay. The initial position of point P is the contact point with the floor. That is, initially the P is in contact with the floor. Draw normal and tangent to the curve at any point. So we also have to draw tangent and normal to the curve at any point of our choice. Okay, we can select that point randomly and draw the tangent and normal. So let us see the procedure to draw this cycloid for this sum. Now we have to draw this circle first of 56 mm diameter. So radius is around 28 mm. So let us draw that circle. mm is the radius for the circle. Now this circle is rolling on a floor which is fixed. That floor can be assumed to be a fixed straight line. So that floor, let us draw that as a line. Now it is rolling for one complete revolution. So what would be the distance traveled by this circle in one complete revolution? It will be equal to its circumference. Okay, so let us draw that straight line initially which is in contact with this circle, and let us draw that line first, and the length of that line will be equal to the circumference of this circle. Circumference is pi d, pi into 56. It is around 175.9. So let us take this as 176 mm. Approximately it is the 176 mm. So this is that straight line. Initially the point of the point on the circumference is at the point of contact. So initially the position of point P is here. What we are supposed to do is that we are supposed to trace the locus of the point P, okay, which is this point initially in contact. So let us show that point. So this is the point P. This point, which is initially in contact with the circle, we have to trace the locus of this point. Okay, I will move it closer to the actual marking. So this is that point P, and this is the circle. It will roll. Let us say that it is rolling in a clockwise direction. Okay, so this circle is rolling in clockwise direction. This is the direction of rotation, and when it is rolling, what is going to happen to this point P? It will follow some path. Okay, relative to this straight line, the circle is rolling, the straight line is fixed. So circle is rolling and it will travels along this straight line. In one complete revolution, this point P will come back again and the circle will reach here. All right, because this is equal to the length of the straight line we have taken is equal to the circumference of the circle. All right, now let us divide this circle into minimum 8 parts or 12 parts for better results. For joining the points properly, it is advisable that you divide it into 12 parts. So let us divide the circle into 12 parts, as well as let us divide this line also into same number of parts. If we divide the circle in 8 parts, the line should be divided into 8 equal parts. But if we divide the circle in 12 parts, then the line should also be divided into 12 equal parts. So let us do that now. For dividing the circle into 8 equal parts, into 12 equal parts rather, we will draw these lines. Lines at 30 degrees. Then 60, then 90 is already drawn. Then 120. And 150. And then we will complete this. Now we have divided this circle. Similarly, we will divide the line into 12 equal parts. How to divide that? This method, you are familiar with this method. So I will just briefly revise this method for you again. First thing, we'll draw another line to this line at acute angle from this point. Angle should be acute angle. Let us take a smaller angle so we can fit it on the page. Any angle which is acute angle will do. Length, let us take approximately 10 mm divisions on this line which is drawn at acute angle. So total length should be around 10 into 12, around 120 mm. So 120 mm, and hit enter. Now this last point, end point, we should join with this end point of this line, first line. And now we will divide this. This is a standard length line, 120 mm we have chosen, and each division will be of 10 mm. So let us divide this line into 12 equal parts and then join the lines parallel to this from those points. Say so like this, 10 mm each. So we will divide this like this into 12 parts and draw lines parallel to this from these points. Okay, so that we will get the equal divisions on this line of which is not of standard length. So now we have got these divisions of this line into 12 parts, and we have named the divisions as well. Now what will happen, see, just imagine that as this circle is rolling on this straight line, when it rolls by 1/12 of the revolution, this P will slightly advance above, and this one will come in contact with this one, first division. Okay, then this 2 will come in the another 1/12th revolution. This 2 will touch this 2, this 3 further, 3 will touch 3, 4 will touch 4, and so on. Finally this P will touch this 12th, because 11th P is again 12th. Okay, P is the starting point and the 12th point here. So gradually, as the circle rolls 1/12 by 1/12th revolution, this P is moving, advancing on the circumference, and lastly when one complete revolution is over, P will again touch the ground here at this location, and this center will traverse along a straight line here, C0, then C1, C2, then on this C3. So let us draw those projectors for all the points for these circles, horizontal projectors, and then trace the path of P on those projectors. So let us do that. First let us do it for the centers. So like this, this is C0, then C1 will be here, then C2, then C3, and so on. So we have named the parts. This center is moving along this line, C1, C2, C3 in that way till the last one, that is C12. Now we will draw the locus of these points also, horizontal lines. One and 11. Ten and 2. And then 9 and 3 already there. Then 8 and 4. Then 7 and 5. And finally 6. So we have got the locus of the points as well. Now you see, just imagine that when this circle is rotating or rolling for 1/12th revolution, the C0, that is the center, will shift its location. It will come here at C1 and P will climb here, okay, on this locus of this line. So one will touch here and P will climb on this line. So for getting the first point of the locus, so just draw the arc with C1 as the center and radius is equal to this radius of this circle. I will switch off these points. So 28 is the radius, which is the radius of the rolling circle, and let us cut this on this locus of point 1. Okay, so this is that point, this point which we got by intersection. We have taken C1 as the center, taken radius is equal to radius of this rolling circle, that is 28, and cut an arc on the locus of point 1 from the circle. So this intersection is going to give the next position of point P when this point on the circumference 1 will touch the ground here. Okay, so that way we will continue getting these intersection points. So now next is C2. We will get this arc from C2. 28 is the radius and locus is for the point 2. Okay, so this is that point. Next point, that is P, will be moving here next in the 1/12th revolution. And then next is the C3, center is the C3 and radius as 28. We will cut on this because locus of center and locus of point 3 is same. Okay, so this is that next point. Then C4 and locus of point 4, which is here. All right. Then C5, locus of point 5, which is this one, 5 point. C6, and locus of 6, that is this. It will be exactly vertical, so let us draw that. It will be the point of tangency only, because this is radius equal to the radius only. So 6th point, and then P will move on this side. Okay, gradually it is going to climb like this, and then it will come on the right side of this center line. So C7, C7, 28, and now don't cut on this side, okay, because P has reached the top and then it will slide down on the right side. It will roll on the right side of this center line. So 28 here on the right side on the locus of 7. This is the locus of 7, this line. Okay, I have done reversely. Okay, I'll do again. C7 and locus of 7. Okay, so this is that point, next point. And then C8, locus of 8. This is the locus of 8. Then C9, and locus of 9. Locus of 9 is same, the center line only. So this is that point. Then C10, locus of 10, then C11, and locus of 11, okay, so this is that point, and finally C12 and locus of 12, you will get the same point. Okay, so that's how we have got all the points. Just mark these points. And now let us join these points by a freehand smooth curve. That curve will be drawn with object lines. and it's a spline. In this AutoCAD software, you cannot join those points with a free hand, but you have a substitute for that. That curve is called as a spline. Okay, B spline. Sorry. So let us join these points now. So this curve is called as the cycloid now, and this part of the sum is over. We have to draw tangent and normal to this cycloid at any point on it. So let us mark any point randomly on this curve. Let us say the point is here. You can mark anywhere. So this point is there. We have to draw now tangent and normal to this point, to this curve at this point. Okay. So first thing is that we will join this point. We have to locate the center. For that, we will take it should be on the circumference of the circle. Okay. First thing, this is a part of the circumference. So we should locate this center when the point is arriving at this position. All right. So this is that point we have marked. For marking the position of the circle, we take the radius in compass, arc, center. We'll take this point as the center and radius as a radius of the rolling circle, and locate that point on the center line. So locate this respective center. Okay, so this is that point. Center, when the center is appearing here, at that time this is the point on the curve. So this center we will project down on the fixed straight line. All right. This straight line is called as a directrix, and this is directing the motion, so it is called as a directrix. So this is that line. We have drawn a line from this new center, and on this join this point from the base on the base to this point on the curve and extend that. Just extend this. So this is the normal. This is the normal. This line is the normal to the curve at the given point. Okay. Now we have to draw a tangent to the same point, to this curve at the same point. So just draw a line which is perpendicular to this line from the same point. So let us do that. I have to use some trick here in AutoCAD. You can draw with a roller scale a line perpendicular to that. When you draw it manually. Okay, now I am using a little trick here to get a tangent line or line perpendicular to the given line. Okay, so that's how we will draw it. So we have got this tangent and normal at the given point. Point we were supposed to choose, so we have chosen it here. Anywhere if we choose the point, the procedure is like this. From the point, take a radius in the compass, cut on the center locus line, and you will get the location of the center. So let us say that this is the location now for this point M. Then draw a vertical line from that center line, from that new center till the base line, that is a fixed straight line. That intersection point is N. Join that point to the given point, extend it. That line is the normal to the curve at the given point M. So N is the normal to the given curve at the given point M. Draw a perpendicular line to this normal line at point M, that is at 90 degrees to this line. That point, this line is the tangent, that is T is the tangent to the curve at point M. So this is how we complete the construction of the sum. And now we'll move to the next sum. So we have got the solution here. Now let us take one more sum of cycloid. A wheel of 60 mm diameter rolls on a horizontal floor for one revolution. Draw the locus of point P on the circumference of the wheel. The initial position of point P is 35 mm from the contact point with the floor. Draw normal and tangent to the curve at any point. See, it's almost similar to the previous one, only now the difference is the location of point P. Draw the locus of point P on the circumference of the wheel. Okay, the initial position of point P is 35 mm from the contact point with the floor. Now this P is not the contact point with the floor, but it is 35 mm away from that contact point on the circumference itself. Okay, so this is that new data for this sum, and the diameter is here 60 mm. So let us attempt this on AutoCAD. See, we have this circle of 60 mm diameter. So this is that circle of 60 mm diameter, and the fixed straight line is equal to the circumference of the circle. This is equal to say around pi into 60, that is around 188.4. So approximately 189 mm we have chosen. And now we will divide this line into 12 equal parts. The method remains the same as the previous one, so we have done that now. And now we have to locate the point, given point. Now given point is not this contact point, okay. The curve we have to trace for the given point and not any other point on the circumference. So just locate this given point on the circumference first. They say that the point P is 35 mm from the point of contact initially. So just take this arc, center is this one, and 35 mm distance, 35 mm. Let us cut this on the circumference. We can cut on the left side as well as on the right side. Since we are assuming that the rolling circle is rolling clockwise, it is easier to cut it on the left side according to the definition. And if you take it on the right side, then you have to assume that the rolling circle is rolling anti-clockwise and the straight line will be here on this side, okay. So these two things are these opposing things. It depends on whatever you are choosing. Since now you have chosen that the circle, rolling circle is rolling clockwise, so it will advance from left to right, okay. When it is rolling clockwise, it will advance from left to right on this fixed straight line. So it is easier to draw the locus of the point P if you choose it on the left side of the center axis, okay. So I choose the point P on the left side of this vertical center line. Choose it here, 35 mm. So P is here, 35 mm from this contact point. So this is my starting point. I have to trace the locus for this point P. Now we have to divide this circle with respect to this P, okay. Don't divide this with respect to this contact point, which we have done for the initial sum, first sum. That was the case because the contact point was the point P. But in this sum, this point P is 35 mm away from the contact point. So we have got the point P here. So with respect to this point P, we have to divide this circle into 12 parts. So let us do that now. Center is not highlighted. So I will join this with the center and then I can extend that later on. Intersection is not highlighted. Is there, okay. Okay, I will stretch this and then later on if required I can trim it aside. All right. So extra part I can trim any time. So let us trim that now. All right. Now this is our baseline. With respect to this, we will divide the circle into 12 parts. So you can draw lines at 30 degrees to this and so on, and then divide this. I will show you directly the divisions. See, we have divided this circle with respect to this point P into 12 equal parts. All right, this is starting from P. And now we will draw the locus of these points horizontally, also the locus of the center horizontally. So these are the projectors from the points for getting the references. This is the starting point P here, and then the centers we have plotted by taking vertical projectors from the divisions on the directing line, that is a fixed straight line. 12 divisions we have got, and from those we have projected vertically up to the center locus and got these different centers on this center line. Okay, now let us number this and then start connecting up, start getting the points on these locuses for that purpose. Now we have given the names to the points starting from P onwards. Now when this is rotating or rolling for 1/12th revolution, what will happen to P? P will here move here, and here another point will come somewhere in between 9 and 10. Okay, so we are not interested in the contact point now. Whatever is the contact point, the P will advance on the locus of these points after every 1/12th rotation, and the center will move to these locations after every 1/12th revolution. Okay, so it is revolving or rolling clockwise. So center will move here. First, after 1/12th, center will come here, C1. So let us take that and draw the arc. So this is the first, and then radius is radius is 30 because this is 60 mm diameter, and let us cut it on the first point locus. Okay, so this is that point P will move from this position to this position after 1/12th revolution. Again, after next 1/12th revolution, so center will be C2, C2, 30 mm radius of the rolling circle, and P will come on the locus of point 2. So P will come on the locus of point 2 here. So right, okay. Then again after 1/12th revolution, center will come at C3. And P will come on the locus of point 3. This is the locus of point 3. So P will come here. Then after again 1/12th revolution, center will be C4 coming here, center will be coming here, C4. Center is going to shift to this location, C4, and the point P will come on the locus of point 4. This is the point 4 locus. Okay. So let us draw that. So it is exactly tangent, vertical, near about. Okay, so this is somewhere here. Intersection is somewhere here. Then after that, it is moving now on the right side. You can see that right side. This is, if you draw vertical contact point line to center vertical, it is moving now. Already it has moved to the right side of that center line. If you just draw it for referencing. So fourth, on the 4 locus, you are getting 2 positions. So this is on the right side and this is on the left side. You have to pick the right one, okay, because it is already moved on the right of the center line. Next, then C5. C5 and on the locus of 5, this is a 0.5 locus line and it is on the right side. Okay, so this is that point. Okay, this is that point on locus of 5. Then C6. And like this, we'll get the locus of that point for all the remaining points. So once we get all these points, let us join them by a freehand curve, smooth curve, and that too with object line. Spline curve. So this is that curve, required curve. Finally, P will reach here at the position again, initial position, and when the center is reaching here after one complete revolution. So this is how the curve is traced, and now we have to draw tangent and normal to any point. The procedure remains the same. So this time let us take the point here, somewhere here, and just complete that procedure. So let us take a point here M, and the procedure is take the radius of the rolling circle in compass, keep the center at M, and cut an arc here on the center locus. So let us call that as the new center O. From that new center, draw a vertical line which will cut the base line or directrix line, and join that point is N, join that point with the point on the curve, that is M, extend that. So this N, M, N is the normal to the curve at the given point M. Draw a line which is perpendicular to this N, M, N from M. So this is T, M, T. This line is the tangent to the given curve. So that's all. The procedure is like this, and we have solved it for the tangent and normal part as well. The complete solution. Next curve is involute. The involute is defined as the locus traced by the points on a tight string while it's being wound or unwound around a circle. So that is the involute, the locus of the points traced on a tight string. The string is tight, and the points on the string will trace the curve, that is called as involute, when that string is either wound or unwound around a circle. And there are different types of involutes. So this is a circle, that's the reason why it is called as involute of a circle. If it is a polygon, then it will be an involute of a polygon. We will only discuss about the procedure to draw involute of a circle. So let us take this example. Draw involute of a circle of 60 mm diameter. Draw tangent and normal at any point on the curve. So let us draw this. Let us see the procedure of drawing the involute. So we have to draw the involute of circle, and the diameter is 60 mm. So we are drawing that circle of 60 mm diameter, divided it the circle into 12 equal parts, and then we are drawn the string or the string which is given, thread which is given for one complete winding. This length of the thread will be equal to the circumference of this circle, so we have chosen that and divided this length into 12 equal parts as like the circle. And now see the it is like that this it is wound, the string is wound around this circle, and gradually what will happen if we wound it for 1/12 of this revolution, one point here will touch here, okay, it will be tangent, then 2 will touch here, 3 will touch here, 4 will touch at the 4, like that, and gradually lastly 12th point P will touch at this point lastly at the end. So we will do that. For that purpose we need to draw tangent at all these points on this circle, and then we'll transfer the location of point P on those tangents gradually. Let us do that now. Okay, I will choose a projection line because these are all construction lines only. See, length you keep approximately, because we will mark exact length by taking the distances for point P. Now what will happen when this point 1 on the line will touch here on the circle, point 1, then point P will be moving along the string, okay, because it is lying on the string itself. So let us take the distance from 1 to P. For that we should first measure the distance from this 1 to this P, and then transfer that from this one onto this tangent. Measure distance from this 1 to this P. It is 171 mm. Okay, now we'll transfer that on this tangent at 171. So we have got the point P here, okay. Then after again 1/12 of this winding, P will be on the tangent at point 2, okay. So let us do that now. Let us transfer that. Measure distance from 2 to P. It is 155. So from these two, we will transfer that 155. Okay, so let us extend this a little bit. So this is that point P at 2. Then again after 1/12 of this winding, these 3 will touch these 3, and accordingly we have to transfer that P there. For that, again we'll measure distance from these 3 to this P, which is 140. Now we'll transfer that from these 3 it was 140. How much it was, I just forgot. I'll again measure that. 3, it was 140. Okay, it is 140 now. $130, so it is here. 140, it is here. Okay. Okay, I have transferred fault wrongly. It is 140. Now it is transferred properly. In the same way, we will transfer the other points. We'll transfer it at other locations. Now 4 to P, this distance will transfer here on this 4 to P, and then 5, and then all this. Since like this we have got all these points, now we will join them with a freehand curve using object line. Line here. So lastly again point P will touch here at the starting point of this line. This is after one complete winding. Okay, so this is the involute. This is that involute for one complete winding of the string, and the length of the string is equal to the circumference of the circle in this case. That's the reason why point P, which is at the end of the string first initially, will come and touch this circle after one complete winding. All right, now we can trim the extra edges and then draw tangent and normal at any given point. Okay, let us take the given point. Since we are free to choose any point, we can choose any point on the curve. Let us choose it here, somewhere here. Okay. Okay, so this is our given point. Chosen wrongly. Okay, so this is, let us say, the given point or any point on the curve. We have chosen this point here. Now, what is the procedure to draw tangent and normal to this curve at this given point or at this selected point? The first thing is that join this point with the center by a line. I think this snap is creating a trouble. So we will join it with the center first. Done. Next, this is that line which you have connected now to the given point with the center. Bisect this line. You know the procedure to bisect the line. So use that procedure. Arc, center, and radius is say more than half approximately. And draw the arcs. On both the sides you have to do that. And now we'll draw similar arcs from this end, more than half. Again, it need not be the same, it should be more than half only. Okay, I have to extend this arc. Alright, so I got this point of intersection of the two arcs. Similarly, here I have to extend this a little bit. Okay, so now I got this point of intersection. Let us join these 2 points, and then that will divide the given line into 2 equal parts. Alright, so I got this division of this point line into 2 equal parts. Now I use this as a center and draw a semicircle. I'll use this as a center and draw this semicircle. It's somewhere like here. Yeah. So I have taken that as a center and drawn a semicircle. Now this semicircle is intersecting the given circle at some point. Let us say that this is that point. So this point is the foot of the normal. So let us mark that point. This is the point, this is the foot of the normal. Let us join this point with a given point, and that will be the normal. This snap is creating a trouble. So this is the normal to the point on the involute. We'll make this with object line. And then we will draw another line which is at 90 degrees to this normal at the given point. That should be the tangent. So this is the line which is perpendicular to the normal, and that's why it is the tangent at the given point. We have named these points as M, and the normal as N, M, N, the tangent as T, M, T. So this is the solution from the slides now. So here the thing to be noted is that the length of the string is equal to the length of the circumference, because they said that for one complete winding of the string, and they are not given any length in particular for the string. Now let us see two variations of this sum wherein the length is given. In the first case the length is less than the circumference, and in the other case the length is more than the circumference. Then let us see the procedure for such problems. Draw involute of a circle of 56 mm diameter. String length is equal to 154 mm. Draw tangent and normal at any point on the curve. See now here, just calculate here the circumference. The diameter is given as 56 mm. So circumference will be equal to pi into 56. It is coming around 176 mm. Around 176 mm approximately. And given length of the string is 154. You see that the string length is shorter than the circumference of the circle. So in this case, what should be the procedure to draw the involute? The procedure remains the same with a slight difference. Now here the P point will not touch at the starting point, or rather the point of contact between the line and the involute, or rather it will end in between, because it is of the shorter length. So let us see the procedure now. See, this is we have drawn now. This is the circle of 56 mm diameter. So 28 mm is the radius. We have divided this circle into 12 equal parts, and we have drawn a line equal to the circumference. It is around 176 mm here. Divided that line into 12 equal parts by the standard procedure. You see that we have to mark point P, which is at 156 mm from this on this line. So from this point we have measured this 156 mm and cut there. From the starting point we have taken the point P at 156 mm. So sorry, 154 mm is the given length. So we have taken that at 154 mm from the point, initial point. So this is our point P on the string, 154 mm away. And now we have to trace the locus of point P. So now our procedure remains the same as the previous sum here. Once we have got the P, now for the first 1/12 of this winding, one will touch here, it will be tangent here. Then we have to take the distance from 1 to P, cut on this tangent. So we'll get this point P here, and then 2 at 2 to P distance, and go on marking the arc. So this point P will move along this track, and this will be connected ultimately. You see that P is lying in between the 10th and 11th division. So here on the circle, it is going to touch the circle between 10th and 11th division. So that is what had happened here. Between 10th and 11th division, it has touched the circle. This winding is complete here. Because of the length of the string is shorter than the circumference, it is ending in between only. So let us now connect all these points with a freehand curve. That will be the involute. So this is the involute. We have joined all the points with a freehand curve with the object line. Now we have to draw tangent and normal at any point on this curve. So the procedure remains the same as the previous sum. I will directly show you. So we have chosen one point on this curve, then join that point with the center, then bisect this and then you will get the center. Using this as a center and up to the center radius, you draw a semicircle. That semicircle is going to cut this circle at one point. That point is N. Join that point with the given point on the involute, extend that, that is the normal. Draw a line perpendicular to the normal at M, that is the tangent. So this solution we have plotted on this slide now. Now one more case we will take wherein the length of the string is more than that of the circumference. And in that case, what will happen? Let us see that and then we will end our discussion there. Now this is that sum. Draw involute of a circle of 60 mm diameter string, 60 mm diameter, it should be a comma there. String length is equal to 215 mm. String length is more than the circumference. Circumference will be equal to pi into 60. So that is around, it is coming to be around 188.49. So around 189 mm, let us take. 189 mm is the length of the circumference and the string length is more than 189, it is 215. So in that case, what will happen for one complete winding? The end point will not touch the circle in one complete winding. It will need a few extra windings so that it will touch the circle. Let us see the procedure for this involute. I will show you directly the solution now in this case. Yes, just see that the procedure is similar to this previous sums. We have drawn the circle of the given diameter. It is 60 mm here. And then we have drawn a line equal to the length of the circumference first here up to this, and then we have divided this line into 12 equal parts. Similarly, the circle is divided into 12 equal parts, and now we have extended this line so that we have to mark P, which is at 215 mm from this starting point. So we have marked that at 215 mm. This is by mistake I have written P here. P is not here. P is here initially at the end of the string. So this distance is from this circle, it is 215 mm. And then at every point on the circle we have drawn tangents and then transfer the distances up to P on those tangents. Okay, that is similar to the previous sums. Only difference is here is this, that P is not ending at 12th division. It is more than the circumference. So we will mark equal divisions on this extra portion of the line as well. So if we go on marking the extra divisions, they just say these divisions are equal. So take this length in compass 11 to 12 and continue marking 12 onwards. So you get 13th division, again you get one more division which is the 14th one. Okay, and P is just nearing this 14th division, not exactly 14th, it is less than 14. So P lies in between 13th and 14th division. So that does mean that P will touch the circumference after one complete winding plus 2 divisions, almost 2 divisions. So let us see that here. After the 12th division, P is here at the 12th division. Okay, so this is the 12th one, this is the 11th one, so P is here, and for the 12th one, this is the 12th one, P is here, and then for the 13th one we'll have P here, 13th, and 14th one is here, 14th one should be there, but it is ending between 13th and 14th. So between 13 and 14 it will end somewhere on the circumference. So that is only the difference here, because the length of the string is more than that of the circumference. The rest of the process is same. So this is the slide for the solution. I hope you have understood cycloid and its variations. Cycloid for a circle rolling on a straight line. So, and its variation you have understood, as well as you have also understood the process to draw involute for a circle and its two variations. I hope this is clear. Thanks a lot for watching these lectures. All the best for your exams.